Hi, this is Sumona, and I've been here for quite some time, and I've been teaching aptitude for quite some time. My students are all across, and they are doing really well in their life. So I'm here to help you to gain success from the very beginning to the end. Let's go hand in hand and understand the basics to advance of mastering aptitude for your interviews. Let's crack it well and do well. So let's understand the agenda of this entire program. So we start with basics of number. This is a module 1. So we start with basics of number. Um, in basics of number, we understand odd numbers, even numbers, and prime numbers, post which we will understand the divisibility rules. So under divisibility rules, we will see how numbers get divided under certain numbers. Let's say how 8 is divided by 2. That's a very short example for it. But then again, we will see how larger numbers can be determined as to which number it gets divided by. For example, if I tell you what is the divisibility rule for, let's say, 4, 5, 6, 7, we wouldn't be able to tell you. But then again, if you know the divisibility rules, you would be able to quickly tell me what if the number is divisible by 2, 3, 4, 7, or whatever for that matter. Next, we will understand remainder theorem. Under remainder theorem, we will first see how polynomials play picture in remainder theorem. I am sure in your previous classes, let's say from 8th grade to 10th grade, you would have come across this remainder theorem, but then we will understand here better as to how polynomials work better with the theorems. Next, we will understand this unit digit and last digit. Again, why is it important? It is important because it tells us the divisibility rules. Let's say I give you a random number and tell you by looking at the unit digit, you would generally be able to tell me if that number is divisible by a shorter number or not. So that's how unit digit and last digit plays a lot of unique role in our entire module. Post that, we will also study about factors and multiples. So factors and multiples meaning, let's say I have 2 into 1 as 2. I also have 2 into 4 as 8. So these are the multiples of 2, whereas 2 is the factor of 8. So we will see this better when we understand factors and multiples. Under this, since we are understanding what are the factors and multiples of each other, we will understand the HCF and LCM and how that is applicable in our daily lives and why are we even supposed to study all of this. So all of these things are going to tell us about this major thing called as LCM and HCF. We will also learn about surds and indices. These are generally going to give us notions about how certain things change with powers and indices, right? And then we will come across a lot of past paper solutions. We will do a lot of problems so that we get better with every advantageous problem. Okay, so first thing is basics of number as we saw in our agenda. First, let's understand what basics of numbers mean. Let's see what the definitions under this, because I told you there are three major things that we are going to study. One is our odd number, then is the even number, then is our prime number. So under odd numbers, so these are numbers that are not divisible by 2. Ideally, let's say there is a number 17. So this is an example. Let's say there is a number 17. We need to check if that number is divisible by 2 or not and identify if it's an odd number, even number, or a prime number, right? So odd numbers can be prime numbers, even numbers can also be prime numbers, but odd numbers cannot be even numbers cannot be odd numbers. So let's say 17. So we know under 2 into 9, we know this is equal to 18. Let's go a step behind. So 2 into 8, this is giving us 16, right? So there is this number which comes between 16 and 18. We are clearly able to see that 17 is not divisible by 2. Hence, we will categorize it under the odd numbers. So 17 becomes an odd number. Coming to even numbers here. So even numbers again, so this 17, again let's take this number itself. I told you it is not divisible by 2. That means it was categorized under odd number. But these two numbers here, 16 and 18, we clearly see that they are multiples of 2, which means ideally if I divide 16 by 2, it is going to give me a remainder of 0, which means 16 and 18 are both divisible by 2. Hence, we will categorize this under even numbers. So 17 becomes an odd number and 16 and 18 become even numbers. Next, let's understand prime numbers. So there are two things that you need to know. Prime numbers are numbers that are divisible by itself as well as 1. So there are two things. They should be divisible by 1 and itself. So that's why we do not consider 1 as a prime number, right? So 1, of course, it is divisible by 1, which is itself. So there is no second category. Hence, 1 is not a prime number. But let's understand 2. Is there any other number which 2 gets divided by? It's just 1 and 2 by 2 itself. Hence, we can say that 2 is our prime number. Let's check 3. So 3 by 1 and 3 by 3. So these are the only two numbers which 3 gets divided by. Hence, 3 is also a prime number. It goes as, okay, let's check for 4. So we will write it here. I know 4 can be divided by 1. 4 can be divided by 4, of course. But I also know 4 can be divided by 2. Hence, there is one extra category here. Therefore, 4 is not a prime number. But we know 5 is a prime number, 7 can be a prime number. But let's see if 17 is a prime number or not. So for 17, I know 17 is divisible by 1. But is there any other number that 17 gets divided by? It's just 17. Hence, I can clearly see that 17 is an odd number, but it is also a prime number. Let's come back to this number 2. 2 is a beautiful number. 2 has a bit of no symmetry, right? Let's understand 2 as a number. So 2, I know it is a prime number. 2 is of course a prime number. But is 2 even or odd? I saw that 2 is even. But there is also one very nice thing about 2. 2 is the only even prime number in the entire number system that we can think of. Because any other number that you get are all odd numbers for that matter. Because any other number which is ideally divisible by 2 should be, a even number. It cannot be odd number. Hence, I can say 2 is my only even prime number. Let's see examples here. So we have different examples. Odd numbers are 1, 3, 5, 7. Next is 9. Next goes 11, 13 and so on. Even numbers are 2, 4, 6, 8, 10, 12, 14 and so on. Prime numbers are 2, 3, 5, 7, 11. See, we did not start with 1 because I told you 1 itself and another number isn't there. So therefore, we will not categorize 1 under prime numbers. Then we go for 13, then is 17 and so on. So these are our three basic categories of number: odd, even and prime. So far we understood what basics of numbers are. Let's next go on to divisibility rules. Divisibility rule is a very important aspect in mathematics for that matter. Anywhere you go when there are numbers to see, you would be, you would want to understand as to how do I fraction this, or fractionalize is a term that we can use in our daily lives, right? So let's say I want to make a quarter of certain number. So we are basically dividing it by 4. So when I take a whole of that number, I would want to know if I divide it by 4, if I get equal shares or not. That's how it started for all of us. If we have siblings, we would want to divide all of that by 2. So we will exactly want to divide it by 2, right? So equal share of a chocolate for that matter. Similarly, divisibility rule plays a very important role in the entire subject of mathematics. Let us understand the key rules. First number is 1. If I have 1 for that matter, so 1 as a number, I know 1 into 2 is 2, 1 into 4 is 4, 1 into 100 is 100. So technically every number is divisible by 1 because it is giving me the same number back. So for it to be a prime number, we saw that it was supposed to be divisible by 1 and itself. So from there we can understand that every number is divisible by 1. Therefore, we do not categorize it with 1. Let us start with a different number, which is 2. To understand the divisibility of 2, you need to know a bit of even numbers, right? So I just told you in even numbers, every number that is divisible by 2 is an even number. That means every multiple of 2 is divisible by 2, right? So it starts with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 and so on. If you see, I know 2 ones are 2, 2 twos are 4, 2 threes are 6, 2 fours are 8, 2 fives are 10. Similarly, 6, 7, 8, 9 and 10, right? But if you see the unit place of these numbers, this can be written as 02, 04, 06, 08 to make it a double digit number. If you see the even places of all this, 2, 4, 6, 8, 0, again 2, 4, 6, 8, 0. Again it continues 2, 4, 6 and 6, 8 and 0. So ideally for a number to be divisible by 2, its last digit is supposed to be even, which means 0, 2, 4, 6 and 8. So these are the numbers in the unit place. If you have any of these numbers, you should know that it is divisible by 2. For example, let's say I have 47, right? In the units place, do I have an even number? I don't. That means this is not divisible by 2. Let us see if that is actually true. So I divide it by 2. I know I know 2 twos are 4, this gives me 0 and I bring 7 down, 2 threes are 6, but I get a remainder which is 1. Hence, I can say 47 is not divisible by 2, which is a clear proof for the first key rule. Let us understand a different number. Let me take 526, a 3-digit number. Again, in my units place, I have 2, which means it should be ideally divisible by 2. When I say divisibility, then I am meaning that the remainder is 0. So let's check if that is true or not. So 2, I know 2 twos are 4, then I bring 1 here, so this is 2. I know 2 6 are 12, so this is 0. I bring 6 down, 2 threes are 6 and my remainder is 0, which means if I divide 526 by 263, then my answer is 2. So this number is clearly divisible by 2. So ideally here the last digit is even, which means it is either 0, 2, 4, 6 or 8. Let us understand the next part, which is 3. For 3, it is very simple again. Let us take a number 5, 6, 2. Right? So what you're supposed to do is, you're supposed to singly sum each of them. So 5 plus 6 plus 2. So 5 plus 6 is 11, 11 plus 2 is 13. So the sum of this is 13. Now, is this number divisible by 3 or not? That is clearly given in our tables, 3's tables, right? So I know 13 is not a number which is present in my 3's tables. Hence, I can say this number is not divisible by 3. Let's check if that is true or not. So 5, 6, 2. 3's are. So I get 3 1's are 3. I will get 2 here, 6 here. The closest to 26 is 8, which is 24, 2 and 2 here, and I get 7's are, which is 21. I get 1 as my remainder. Hence I can say 562 is clearly not divisible by 3. Let's check a different number which can be divisible by 3. Let's give 270. 270 is a number, so singly add all of them. 2 plus 7 plus 0, so this is giving me 9, which means 9 is divisible by 3. Hence, I can say 270 is divisible by 3. Let's again check it. So whenever there is something in mathematics, you should always have this possession of questioning if that is true or not. If yes, why? If no, why? Why not? Right? So that's when you will understand. Hence, I am showing you all of these proofs. So I divide this by 3. I know I can't take the first number. Hence, I take two numbers. 9's are 27. I bring 0 down. 0's are 0. Hence, I know it is divisible by 3. So 270, I clearly have the proof that it is divisible by 3. So for divisibility by 3, you are supposed to singly add all of them and check if the number that you added off to is present in the 3's table or not. That's it. Coming to divisibility by 5. Let's take a different number so that you don't get bored. So ends with 0 or 5, which means the unit digit is either supposed to be 0 or 5 for that matter. Let's take 25. I know I clearly have this in my 5's table. So 5 here, right? Let's check 625. Right? Again, in the units place, I have 5. Let's check if it's true or not, because I told you, you should always question. So 5, 1's are 5. I get 1 here. I have to bring 2 down. 2's are 10 here. I get 2. I get 5 down. 5's are 25, giving me a remainder of 0. That means 625 is clearly divisible by 5. Let's take a different number. Let's check if that is not true, right? Let me take 1028. In the units place, I do not have 0 or 5. Let's check. So ideally, this is not divisible by 5. Let's check if that is true or not. So 5. Now 5 2's are 10. I bring 2. I can't divide 2 by 5. So I will write 0 to bring the other number down. So 28. So the closest is 5, which is 25. It is giving me 3 as my remainder. Hence, 1028 is not divisible by 5. Similarly, I can see it's either 0, so this number here that we get is clearly divisible by 5 because 5 is in my units place. Next is 7. 7 is it's not tricky, it's just a little, you need to understand it better. So, you need to double the digit, subtract it from the rest of the number and then check if it is true for that. Let's take a number 798. So first is double the last digits. So that is what is written here. Remove the last digit of the number and double it. So you remove this 8. So when you double 8, it becomes 16. And then you will subtract from the remaining number. The remaining number here is 79. Subtract 16 from 79. So 3 and 6. You're going to get 63. Now, is the number 0 or recognizable 2-digit multiple of 7? Is this a multiple of 7? Yes, because I know 7 nines are 63. Hence, I can say this 798 is divisible by 7. So, it's clearly here, yes, divisible by 7. No, then you again repeat from it. So, what do you do again? You will again remove this number, double it, subtract from this number, and then check if it's divisible by 7 or not. If you get 0, then also it's divisible. If you don't get 0, then you will check if it's a recognizable 2-digit multiple of 7. If yes, if it is divisible by 7. If no, it is not. So let's check if this 798 is actually divisible by 7 or not. 798, I have 7, so ones are 7, 0, I bring 9 down, ones are 7, 2, I bring 8 down, I know 4s are 28, so this gives me 0. That means 114 is my quotient. That means this 798 is clearly divisible by 7. So we saw 4 key rules. For number 2, I told you the even place or the unit place is supposed to be 0, 2, 4, 6 or 8. If so, yes, it is divisible by 2. Next, you take 3. For 3, you have to sum each digit and check if it's divisible by 3 or not. That is, it is present in the tables of 3 or not. If yes, then yes. Then for 5, it will either end by 0 or 5. For 7, you have to double the last digit, subtract it from the rest. If it's a recognizable 2-digit multiple of 7, then yes. If not, you will again repeat the steps. So that is the key rules for 2 to 7. Now I clearly told you for 1, every number is divisible by 1. Why aren't we checking for 4? We are not checking for 4 because ideally every number which is divisible by 2 should be divisible by 4. Ideally that should be the case. And next 5 to next I have 6, right? So 6 is a multiple of 2 and 3. So every number which is divisible by 2 as well as 3 will be divisible by 6. Hence we are mainly checking for all the prime numbers here, if you notice. So we understood from 2, 3, then we saw 5, we also saw 7. Let us understand a little bit more about 8. So for 8, we need to see that the last 3 digits of a number are divisible by 8. Let's say I have 8064. I know this number is divisible by 2 and 4 both. If this number is divisible by 3 or not, for that the last 3 numbers we should check if it is divisible by 8 or not. So 064, I know 64 is clearly divisible by 8 because 8 into 8 is 64. So hence this entire number is divisible by 8. Let us understand the divisibility of 9. It is very similar to 3. Only thing is, now instead of checking the sum after you individually sum all of that, and in the finally you will check if it is divisible by 3 or not. Here you check if it is divisible by 9 or not. For example, let's say I have 8100. So this is a number here. I will singly add all of this, 8 plus 1 plus 0 plus 0. So this is going to give me 9. Is this number divisible by 9? Yes, of course it is. Hence, I can say it is divisible by 9. For divisibility of 10, it is again pretty simple. In the units place, last digit is 0 because I know in the tens table all the last digit numbers are 0. 10, 20, 30, 40, all the unit places are 0. Hence for 10 it is very simple. If it's divisible by 10 or not, you just need to check if it's 0 or not in the units place. For 11, again it's a bit tricky. So here it says sum of digits in the odd place minus sum of digits in the even place, and finally you get 0. So there's a better way to understand this. Let's take a different number. Let's say I have 1331. Also, fun fact, this is known as a palindrome. Palindrome are numbers or words you read, front to back and back to same the same. For example, there is also Nitin, right? If you see, this is Nitin, Nitin. So this is known as a palindrome. Anyways, coming back to our main agenda, understanding divisibility by 11. First, what you do is start with negative. 1 minus 3 plus 3 minus 1. So 1 minus 3 is minus 2. Minus 2 plus 3 is 1. 1 minus 1 is 0. So my final output is 0. Hence this is divisibility approved, which means 1331 is divisible by 11. Let's check if it is true or not. So 1331, let's say I have 11 here. I take, so 13 ones are 11 here. So I have 2, 3, 2s are 22, and then I'll get 1. I bring 1. I know it is 1 again. So 11 and then 0. Hence I can say 1331 is very much divisible by 11. So all you have to do is first any number. Let's say the number is X, Y, Z, A, B, right? So this means it is a 5-digit number. So first you start with negative X minus Y plus Z minus A plus B, and finally if the output is 0, then it is divisible by 11. So let's quickly summarize this slide. So divisibility by 8, the last 3 digits are supposed to be divisible by 8. Next, for 9, you check, you add all of the numbers, and if the final number is divisible by 9, then it is divisible by 9. The entire number is divisible by 9. For 10, the units place is supposed to be 0. For 11, sum of odd places minus sum of even places is supposed to be 0, or ideally minus plus alternatively, and finally you get 0. So this is about your divisibility. So let's understand practice questions now. Very much into it. So I hope all of you have understood. Let's quickly recap. For 2, the unit digit is supposed to be 0, 2, 4, 6 and 8. For 3, you need to sum each of the digits and finally check if the number is divisible by 3 or not, or a multiple of 3 or not. For 5, the unit place is either supposed to be 0 or 5. For 7, you need to double the unit digit, negative of the rest of the number, and if it's a multiple of 7, great. If not, repeat, right? Then we have 9. For 9, we saw each of the digit you have to again singly add all of it, check if the final output is a multiple of 9 or not. For 10, we saw each unit digit is supposed to be 0, and for 11, alternatively minus plus, final output is supposed to be 0 for that matter. Let's understand this number now, 2145, if it's divisible by 3, 5 or 7. So 2, 1, 4 and 5. First, we are supposed to check if it is divisible by 3 or not. For divisibility by 3, I told you again, each number is supposed to be added. So let's add 2 plus 1 plus 4 plus 5. So what is this going to give me? 2 plus 1 is 3, 3 plus 4 is 7, 7 plus 5 is 12. So 12 is a number which is divisible by 3. Hence, this number is divisible by 3. Next, let's come to 5. For 5, the unit digit is supposed to be either 0 or 5. I know it clearly has a number 5. Hence, 3 is done, 5 is also done. Coming to 7, it can be a little confusing when you're initiating your studies, but then once you keep practicing more, it becomes very simple. So here 2, 1, 4, 5 divisibility by 7. For that, I told you first remove the units place and multiply it by 2. So 5 2s are 10. Now you have 214, subtract 10 from 214. 204. Is this number divisible by 7? I don't know, because I only know numbers from only till 70, right? 7 ones are to 7 tens are is all I know. So I don't know this. Next, again check. Now my number is 204. Correct? Now remove this part again. Right? So you remove 4. Sorry, 1 second. So I had 204, this I don't know. So let's bring back this number 214, right? Now again, remove this number, multiply it by 2. 4 2s are, I know it's 8. So 21 minus 8. How much is 21 minus 8? Any idea? So that would ideally give me 13, right? So 13 divisible by 2 because we are ideally going to get a 2-digit number, because even in our previous slide we saw it was supposed to be a 2-digit number. Is 13 divisible by 7? Of course not. Hence I can clearly say that 2145 is a number which is not divisible by 7. Let's come back. So here we saw that it is divisible by 3, 5 but not 7. Divisible meaning remainder is not 7. Of course you can divide that, but you will get your numbers in decimals. Next, understanding determination of 7, 2, 5, 4 by 3, 7, 9 and 11. Great. So let's understand 3 first. 3 is very simple. 7 plus 2 is 9. 9 plus 5 is 14. 14 plus 4 is 18. 18 is a number which is clearly there. So the addition of this number is 18. Right? So 18 is divisible by 3. Hence, yes. For 7, what we have to do again. So 7, 2, 5, 4. First multiply it by 2. You get 8. 725 minus 8. So again here we can't do it, so we borrow a number. 15 minus 8 is 7. So I will write 1 back. 217. 217, I don't know if it's divisible by 7 or not. Hence we are not going to take that number yet. Sorry, 717. Not that. So we don't know that yet. Next we take here 725. So 5 multiplied by 2, so we are going to get 10. 72 minus 10 is 62. Is 62 a multiple of 7? Of course not. Hence this number is not divisible by 7. Next, checking for 9. 9 is pretty simple. We already have the addition of it, which is 18. Hence it is divisible by 9. Next, let's check for 11. For 11, I told you, you are supposed to alternatively negative and positive for that. So 7, 2, 5, 4. Start with negative, positive and negative, right? 7 minus 2 is 5. 5 plus 5 is 10. 10 minus 4 is 6. So my final output is 6, which is not 0. Hence, it is not divisible by 11. Let's move on to our next topic, which is our remainder theorem. Remainder theorem, ideally, I know, let's understand a bit about remainder theorem. So remainder, the word suggests we have this, right? So when we divide, we have a divisor, we have a dividend, we have a quotient, and finally this is our remainder, right? So this remainder theorem tells us, using this, how can we solve the problem of these three. So that's what our remainder theorem does. So let us understand as to how this remainder theorem works, right? So first thing is, when p of x is divided by x minus a. So p of x here ideally is a polynomial. What is a polynomial again? So polynomials are, let's say, in the form of ax square plus bx plus c equals 0, right? So these are polynomials where it has degrees. It again, when it doesn't have a degree, that means it is 1, and if there's nothing, that means it is x power 0, because anything power 0 is 1 mathematically, right? So these are our polynomials. So when this is divided by a linear polynomial meaning the power is supposed to be 1, like for this one. Let's say x minus 1. So this is a polynomial, of course, but with what? Power 1. So highest power in that particular expression is supposed to be 1. It can also be an equation. Before I go into this, let us understand two things. One is expression, another one is equation. When it comes to expression, right? So expressions do not have an equality symbol. For example, ax square plus bx plus c. If I write just this, it becomes an expression. We are expressing the numbers, right? But if I write the same thing as ax square plus bx plus c equals 0, this becomes an equation. Why? Because I am equating it to something, but here we are just expressing. So expression and equations are two different things. So this is something that you need to know a little bit about, right? Now coming back to our remainder theorem, we just saw something about our linear polynomial here, right? So in a linear polynomial, the highest degree is supposed to be 1. So I hope so much is understood. We will move on as to all of this is fine, but then we wouldn't know how to apply all of this. There is a very simple way of it. So if you see, we have this. When p of x is divided by x minus a. Now p of x is a polynomial. X minus a is also a polynomial, but what is it being divided by? A linear polynomial. So here the highest degree is 1. Now the remainder for this, when you divide a polynomial by a linear polynomial, the remainder is basically the polynomial with the value of this a here. Understood? So for example, let's say x minus 1 equals 0 is my equation. So from here this becomes x is equal to 1. So instead of writing as p of x, we write it as p of 1. So the whatever value for this we get becomes for p of 1. So this is only when we have x minus a. But when we have something more to it, like for example, we have ax plus b. Ax plus b is also a polynomial with a degree 1 here. This, if I convert it into an equation, convert it into an equation, ax plus b equals 0. This is going to give me x is equal to minus b by a. That is what is written here. The remainder would be a final product of p of minus b by a. So that is how you understand the remainder theorem. So now let us understand by an example. So in the first remainder part, you saw it was p of just a, where this was on the form of x minus a. Right? So this x minus a plus a, it is really not necessary for us to understand all of that. It is simply negative into negative becomes positive. Here I have negative into negative, hence that became positive, which means the value of x currently is just minus 1. So let's understand these by two forms. One is our long division method, another one is the remainder theorem. Let's see how quickly we can come to which part of it, right? So first part is our remainder theorem, long division. Okay, so first let's understand long division. For that, we know dividend. What is dividend? Dividend is whatever is written here, right? This part is known as a dividend. This is our divisor, right? So let us do our division part and check if it's actually true or not, right? Of course, it would be true, but then let's just try and find out the proof for it. So x square plus 2x plus 1, and I have x plus 1. So while dividing polynomials, it is a little tricky because we have to consider all of these into pictures. So first thing what you do is you take this up, right? You write it in the left hand side. I have x square divided by the first term here. So you get x. I know x and x gets cancelled. Whatever the term you get here, write the same thing here in the quotient part. Whatever you get, it doesn't matter if it's a fraction also, right? Now what you will do, you will multiply this into both these terms. Now start by multiplying the first term. X into x is giving me x square. Next, minus, I don't have a minus here, so plus into plus. When I don't have anything, that means it is a positive sign. Positive into positive will give me a positive. Next, x into 1 is simply x, right? So now after this, we know in division we always take a negative. So when we have polynomials, to take negatives, we make it a negative. We change the signs. So positive here becomes negative, positive here becomes negative. So we do that for each term in polynomials. So this gets cancelled here because it is positive x square, negative x square gives me 0. Now here plus 2x minus 2x is simply plus 1x. And whatever you have here, bring it down, plus 1. Right? So I have x plus 1. Again the same thing like here. First take this term x divided by the first term here. So x and x gets cancelled. This is giving me 1 and it is plus 1 because I don't have a sign there. So plus 1. Now multiply 1 into x, which is x, 1 into plus 1, which is plus 1. Change the signs, you are getting a 0. That means by long division, my remainder, so this is our remainder, this is called as our quotient. So this is our dividend, this is our divisor. So our remainder from long division is basically 0. Let's check if that's true for the remainder theorem as well. So for remainder theorem, what are we supposed to do? We are supposed to take, let's say, okay, let's clear this off. Let's understand in a big screen so that it would be easier for all of us. So now here, coming to the remainder theorem. So in remainder theorem, it says we are supposed to convert this value and then put it in this equation, right? So x plus 1, so for x minus 1, it was simply p of a. That means negative turned into positive. So for positive, it would turn a negative. That means p of minus 1. Right? So now here we have to apply this value here because this is our equation. So we have p of x as x square plus 2x plus 1. Let's see what is p of minus 1. P of minus is minus 1 whole square plus 2 times minus 1 plus 1. So minus into minus is 1, a positive 1, minus 2 into minus 2 is minus 2 plus 1. So 1 plus 1 is 2, 2 minus 2 is 0. So using remainder theorem also our value is 0. So technically remainder theorem helped us shorten our entire value down. So instead of doing the entire long division, going through the process of hassle of dividing x square by x, multiplying all of that, instead of all of that, it was very simple for us to simply use the remainder theorem, which is the divisor's value for a negative, because x minus a, it was p of a. So if it becomes x plus a, it would ideally be p of minus a. In this case, plus 1 becomes minus 1. And you put the value of it in the polynomial that was given to us and finally arriving at the remainder of it, which was 0. So ideally, remainder theorem was much easier for us to come to the final solution. Let us see the same thing for a different equation now. So now here, I have a huge polynomial given to me, I have the divisor. Now here, this is in the form of ax plus b, right? In the remainder theorem, we had two things. One is x plus a, another one, x minus a, another one was ax plus b. Now we will understand the second type. So for this, first we will again do the same thing, check by the long division method, check what is our remainder. Next we will come back to the remainder theorem and check what is our remainder. For this, what will I do? Again, 6x power 4 minus x cube plus 2x square minus 7x plus 2. If you see, this is going to consume a lot of time from us to find the final just one sort remainder of when you divide by this 2x plus 3. Nevertheless, let us try. So 2x plus 3. First thing is you divide this by this. So 6x power 4 divided by 2x, x gone, this gives me 3 here, 2 ones are, 2 threes are. So 3x cube, right? 3x cube. So this is going to give me, now multiply 3x cube. So 6x power 4, 3x cube plus 3, that is giving me 9x cube. Right? So now negative, because we have to subtract, this goes off. Now 9x cube, minus 9x cube and minus x cube. So that is giving me minus 10x cube. Right? Now bring this number down, 1 by 1 plus 2x square. Now again, minus 10x cube divided by 2x. So x and x here square goes off, 2 ones are, 2 fives are. So this is minus 5x square, minus 5x square. Let me write the same thing here so that it becomes easier for us. 3x cube minus 5x square. Now multiply minus x square. So this is giving me minus 10x cube, and minus into plus is minus, which is giving me 15x square. Right? Now what you have to do, you have to again change the signs. So this becomes plus, this is also plus, this goes off now. Now here I have a positive, I have a negative. 15 minus 2 is 13, so 13x square. Next, bring this one down, which is minus 7x. Right? Now if you see, until now these were divisible by 2, but here I clearly cannot divide it by 2. So for that, what will we do? Again, we get a fraction. So 13x square divided by 2x. X and x gone here, 13, and it has to be kept the same. So this will be written as plus 13 by 2x in the quotient part. Now multiply this with 2x, it is going to give me 13x square minus, sorry, this is plus only, right? So plus 13 by 2x into, I have 3, so 13 3s are 39x by 2. So this becomes 39x by 2. Now this is negative, this is also negative, this goes off. Now you have to use the fraction method to solve this. So I have minus 39 by 2 minus 7, all of this with an x, or ideally if I take minus out, so this is 39 by 2 plus 7 into minus x. So for this will be 39 plus 14 divided by 2, which is ideally equal to 13 and 1 goes, so 53 by 2. So minus 53 by 2x is our final solution for this. So this gave me minus 53 by 2x, and finally I have to bring this 2 down here, which is plus 2. Right? So there is a lot of hassle in the entire solution. If you see, you are getting fractions, you're doing all of that. Let's complete the problem and check what our remainder is. So all of this is happening, right? So instead of all of this, we are going to get directly to the remainder. How? By simply putting the value of it, right? So instead of doing all of this, we can simply come to this. So let's understand this. So for this, I again have to minus 53x by 2 should be again divided by 2x, right? So x and x gone, minus 53 by 4 is what I'm going to get. Minus 53 by 4. This part is gone. Now multiply that. You're going to get minus 53 by 2x. Next, you have to multiply minus 53 by 4 into 3. Now 3 3s are 9, 3 5s are 15, minus 159 by 4. So this is minus 159 by 4. Let me write this part here for your better understanding. So this part goes off because we have to again negative, this becomes positive, this is gone. So this is ideally 159 by 4 plus 2. So 159 plus 8 by 4, which is going to give me 167 by 4. So my final remainder is 167 by 4. So to do all of this, again, what did we do? We had to go through so much hassle, right? So this was by long division. So we understood about the long division part that we were doing. Let us now use the remainder theorem to get the remainder in a very easy manner, right? So for that, P of x is given as 6x power 4 minus x cube plus 2x square minus 7x plus 2. And our divisor is 2x plus 3. So this ideally x value would become minus 3 by 2. So here P of minus 3 by 2 would be our main agenda. So to do that, we will simply for P of x, I know P of x is what? 6x power 4 minus x cube plus 2x square minus 7x plus 2. So this should ideally be P of minus 3 by 2, which is going to give me 6 times x power, so this would be by 2 whole power of 4 minus 3 by 2 whole cube plus 2 times minus 3 by 2 whole square minus 7 times minus 3 by 2 plus 2. So let's check if we get the same answer. We will get the same answer. So 3 power 4 means you have to multiply it, right? So 3 into 3 into 3 into 3, 4 times. So 3 3s are 9, 9 into 9 is 81. And since I have negative here, any time when you see a even power, you should know negative changes to positive. When it's odd here, negative remains negative. So this becomes 6 times. I have 81 divided by 4 4s are 16 minus, why did I do 4 4s are? Because I know 2 power 4 is ideally 2 into 2 into 2 into 2. So from here 4, from here 4. So directly I took it as 4 into 4 as 16. Okay, coming back to this part, minus, I have again, so I will get a minus here, so this will become positive because I have a odd power here, and odd, this minus into minus will give me positive. So 3 power 3, so you should know the cubes from 1 to 10 at least and squares from 1 to 30 at least to make sure that your aptitude is better. So now 3 cubes are generally 27, 27 by 2 cube is 8. Plus, now this negative becomes positive. So I have 2 into 3 square is 9 by this becomes 4. Minus, now I have minus here, minus into minus becomes plus. 7 3s are 21 by 2 plus 2. Now remember, whatever you can cancel, cancel. Whatever you have to keep as it is, keep as it is. So I know 2 3s are 6, 2 4s are 8, sorry, 2 8s are 16. 2 8s are 16. I have 2 1s are here, 2 2s are. So I will write this above there. So first let's multiply this off. So 3 1s are 3 and 3 8s are 24. So this will be 243 divided by 8 plus I have 27 divided by 8 plus I have 9 by 2 and then I will have 21 by 2 plus 2. Now how will you solve this? Like fractions and unlike fractions. So first solve the like fractions part. So for this I will have 8, 243 plus 27, I will have 10 plus 1, 6, 7 and 2. 270 by 8 plus, so 9, this will give me 30 by 2 plus 2 here, right? So 2 ones are, 2 15s are, 2 fours are, and this is divisible by 2 because it has 0 here. 2 ones are, 2 threes are 6 and 1 carried, so 5s are. So I have 135 by 4 plus 15 plus 2 is ideally 30, right? So now take an LCM, LCM would be 4. Now 135 plus, you will multiply this here, 4 into 120, which is 120 here. So ideally it is giving me 255 by 4, which was again very simpler using the remainder theorem. All you had to do is simply put in the number and make sure your entire values were dependent on that. That's it. So this is my final solution for the remainder theorem for this particular problem. So we have another problem to understand the remainder part, how to find remainders, how to go about it. So now we have, the number is 4, 5, 6, 7. We are supposed to find the remainder when this number is being divided by 13. For this, you need to know the tables of 13, of course. So let's say 13. First thing is, you have to find out the closest number to be divisible. So I know 13 threes are 39 because next number goes to 50. So this is 39 here. You have to negative. So this is 6 and then you take one number, 66, right? I can take 13 fives are. So 13 fives are 65. So from here I get 1 and I will bring this 7 down. So 7, 13 ones are 13, right? So minus, this is only going to give me 4, right? So the remainder directly is simply for this small kind of numbers, right? Let us also understand the next part. So I have, if a number leaves remainder 7 when divided by 12, what is the remainder when it is divided by 12, right? So it is very simple again. So there is a number, that is what they are trying to say. There is a number, this number leaves a remainder. So you know what is a dividend, what is a divisor, what is a quotient and what is a remainder. So it is leaving a remainder of 7, correct? When it is being divided by 12, that means there is a number, let's say x, that is being divided by 12. The remainder that we are getting is basically 7. So much is understood. Now what will happen? What will be the remainder when it is divided by 12 again? So the same thing, it's pretty simple, it's the same thing given to you, but then you just have to understand what is given to you. So the tricky part here is, so to do that, this is a past paper question. So anyways, let's first decode this. To decode this first, I will make you understand one situation. Let's take a number 63, right? 63 can be written as 7 into 9 plus 0, right? So this is my dividend, this is my divisor, quotient and a remainder. So what am I doing? Our dividend is equal to quotient into divisor plus the remainder. So this is again a very generalized form of remainder theorem for number theory that we are using, which is our aptitudes. So here, so when I am dividing 63 by 7, my quotient is 9, right, or vice versa, and my remainder becomes 0. What happens if I divide, if I keep this same, right? So 64, let's say, is being divided by a number 7, right? So our divisor right now is 7 into, this is again 9. 9 is our quotient. This is our quotient. This is our divisor. Plus I will get 1 as my remainder. Right? Ideally that should be the case. Let's check if it is yes or not. 64 is being divided by 7. 9, 63. I will get remainder as 1. So remainder is 1 here. So what did you understand from here? When you multiply these two, you are either going to get this and a remainder becomes 0, or if you get some sort of remainder, this should be either more or less. Less meaning you will get a negative. Since I don't have a negative, we will say it is more than the number it is ideally supposed to be, right? So for that what did we understand? We saw, let's say I have P, let's say this is Q, this is, sorry, let's make it very simple. Let's say this is D, this is X, this is Q, and this is R, right? If I have to simplify this and write, I am going to get D is equal to XQ plus R. We will apply the same logic to this particular problem as well. So they are telling us that, let me write this here for you. So dividend would be n into q plus r, where n is our divisor, d is our dividend, right? So the same thing here, they are saying there is a divisor, I don't know what that is being divided by 12. And I don't even know what is my quotient. So I will keep this quotient as it is. Plus remainder is 7. Right? So this is basically the equation that we are going to get from here. Now what is our final equation? What will be the remainder when it is divided by 12? Again, when it gets divided by 12, I am going to get the same remainder as 7. It does not change, right? So the remainder, final remainder is again 7. So this is a one-liner if you know this equation here. Next, moving on to unit digit and last digit. For that, you need to understand what is the relation between this unit digit and last digit. Unit digit is basically the last digit of a number. For example, let's say I have 1, 2, 3, 4, 5, 6. This is my number. What is our unit digit? This is our last digit, which is 6. I hope that much is understood. If that is understood, let's understand what kind of patterns are seen, right? So I have powers of 2, powers of 3, powers of 4 and so on, right? Powers of 3 meaning there is a repetition here. What is that repetition? So if you see, let's say I have 2 square. 2 square is going to give me a 4, right? 2 power 1 is simply 2. Again, 2 power 3 is 8. 2 power 4, what do you think that could be? That is simply 16, right? Next, 2 power 5 is again the square of this, multiply by 2, which is 32. 2 power 6 is again 64 and so on, right? So the pattern here that you are seeing is 2 power 1, the unit digit is 2. 2 power 2, the unit digit is 4. 2 power 3, unit digit is 8. 2 power 4, unit digit is 6. 2, 4 and so on. So after this, it is a repetition. That means I am getting 2, 4, 6 and again 6 I am getting, right? So basically it's just 4 digits, 2, 4, 8 and 6. It repeats, it keeps repeating as and when you keep multiplying by that number. So the repetition means the last digit being the same, right? Similarly for a number 3, right? Let's say I have 3 power 1. 3 power 1 is 3. 3 square is 9. 3 cube is 27. 3 power 4 is 81. And 3 power 5 is 243. So if you see all your numbers here, units place is 3, 9, 7, 1 and again 3, 9, 7, 1. That's how it keeps repeating. So there is a pattern here, 3, 9, 7, 1. Similarly, for 4, 5, you have patterns like that. For 5, ideally it's just 5, right? So that is how units, place and last digits are there. There are different types of patterns as well. So when you multiply a number by 2 or a number by 3, so that's how patterns change, right? So you saw the patterns. So for squares it was different, cubes it was different. Similarly, in tables also you see different types of patterns. Like for example, 2's table generally has 0, 2, 4, 6, 8. 3 generally has 3, 1, 8, similar to, sorry, no 8 there. Yeah, of course we have 8 because we have there, right? So we have 24 as well, we have 21 as well. So numbers like that are present in the units place. So whenever you see a number, you should be ideally able to tell as to what number it could be a multiple of, right? Next, coming to the next topic, which is factors and multiples. So far, so on, I have been telling you what is, something is a factor, something is a multiple. Let us now understand as to what exactly these factors and multiples are, right? So factors and multiples, first thing is, you need to understand these definitions before digging deep into HCF and LCMs. First, factors and multiples. What are factors? What are multiples? Factors generally start small. So, for example, let's say I have a number 6 and I ask you what is the factor of 6. Factor meaning you multiply something to get that number. So, for example, if my number is 6, what are the factors? I can multiply 1, there is 2, there is 3 and there is the number itself, right? So I multiply 1 into 6, I will get 6, I will multiply 2 into 3, I will get 6. But if I multiply 2 into 6, I am not going to get the factor, right? So these individual numbers are factors of 6. Next, coming to multiples. What are the multiples of 6? You multiply 6 with any number. So 6 itself is a factor because I am multiplying that by 1. Next, you multiply that by 2. So 12. Next, I am going to get 18. Next, there is 24 and so on. So multiples meanings you are multiplying something to this number, and factor meaning what were multiplied to get back that number. So that is the main difference between factors and multiples. Now coming to our main topic, which is factors and multiples, HCF and LCM. First, let us start by understanding the definitions of HCF and LCM. HCF meaning highest common factor shared by numbers, right? That means HCF comes from this H, C and F. So that is the highest common factor. LCM meaning smallest multiple which is common to different numbers. Let's say I have two numbers here, let's say 18 and 24. So for these two numbers, what is the highest common factor? That means a factor, there is one factor, right? I told you each individual number is a factor. So for these two numbers, what is the highest factor that can go on? Similarly, LCM meaning what is the common multiple? The smallest common multiple, right? So highest common factor, lowest common multiple. So that's how HCF and LCM works. So before I try and understand this entire experience of HCF and LCM, I would first want to know why do I have to study all of this, right? So for that we have the real life applications for HCF and LCM. LCM, it says scheduling events like traffic lights changing or intervals to minimizing waiting time. Why? Because we have four different factors, right? So we have four different ways. That's when a traffic light comes into picture, right? So we have to understand what is the pattern of it going. So one after the other, it starts changing. So as and when AI started coming, it became easier for us. So basically, it is the LCM that was used to make sure that it was going in a proper manner. Next, again, in LCM we say in making products with uniform dimensions like cutting multiple sheets with smaller identical pieces, right? So small, how many pieces are we supposed to cut? That is the lowest common factor, multiple. Next comes HCF, dividing resources evenly such as distributing 12 apples among 4 baskets without cutting any apple. So there are how many baskets? There are 4 baskets, there are 12 apples. So each can have how many? Ideally 3. So I didn't have to cut any of the apple there, right? Similarly, finding the largest size of equal size tiles to fit a floor. So to fit these floors that you see in your houses or anywhere for that matter, all those were done using the HCF. Let's understand the working of it. For HCF, let us take two numbers. Let's say this is for HCF, I have a number 18 and 24. I am asked to find what is the highest common factor for 18 and 24. For this, you should know prime factorization. Prime factorization is very simple again. You are simply dividing the number only by prime number. So that's why the name prime factorization. Factorization meaning finding the factors, right? So let's understand the factorization of 18. The lowest number is 1, which it can be factorized by, but we will get back 18 again, right? So therefore we start with 2. 2. Now 2 words are 19, 2 9s are 18, right? Now I know 9 cannot be divided by 2, therefore I will take the next number, which is 3. Next 3 3s are 9 again. Now 3 1s are 3. So this is how it works in a triangle like this, right? So 3 1s are 3, 3 3s are 9, 2 9s are 18. So that's how it works. So what are the factors of 18? I saw it is 2 into 3 into 3. Now we will find out what are the factors of 24. It's pretty simple again. For 24, it's simply again start with 2. 2 12s are 24. Again, next 2 6s are 12. Next again 2 3s are 6. And then I have 3 1s are 3. So the factors of 24 are 2 into 2 into 2 into 3. While finding the highest common factor, make sure you are keeping them one above the other, right? So 2 into 3 into 3, it is only for your convenience, nothing else. So in 2 into 2 into 2 into 3, right? Now here you have to check what is common. There is one common, which is 2. There is another common, which is 3. Nothing apart from that is common, because I have 2's here, I have 3's here. So what is our HCF of this? Which would be 2 into 3, which is 6. So 6 becomes my HCF. So understand, let me write it here. HCF of 18 and 24 is 6. But that is not the case in terms of LCM. Let us try and understand the working of LCM. LCM of, let's find the same number 18 and 12. 18 and 24. So for this, you take both the numbers together. So this is 18 and there is 24, right? Now you take a number, you divide both of them by that number. So ideally, let's take 2. Let's start with 2. 2 9s are 18, 2 12s are 24. Next, I can take 2 again, right? So 2, I don't have a multiple of 9, therefore I keep 9 as it is, and then I go 2 6 are 12, and then 2. I don't have a different number for 9, I will continue it here. 2 9 and 6 is what I am left with. So 2, I don't have any 9, so keep 9 as it is, and 3, right? Then I have 3 1s are and 3 3s are, 3 1s are and 1s are. So you have to continue it until you have 1 and 1. So what is the major change here? The major change was when I don't have a factor of that, I will directly write the number as it is. When I start having factors, I will simply write whatever I get. And in the end, if you have 1 already, simply write that 1. So now what is the LCM? For LCM, all you do is you multiply all of these numbers. So 2 into 2 is 4, 4 2s are 6, 6, okay. then you have these two, which is 9. So technically it's 8 into 9, which is, so LCM of 18 and 24. So what did I get? 2, 2, 2, 3 and 3, which is 8 9s are, which is 72. That means that is the lowest common factor that could have been, that could come out of 18 and 24. So if you see, HCM is 6, sorry, HCF is 6, whereas LCM is 72. So that's how it changed, right? So we took an example of 18 and 24 already. So I hope you have understood that. Make sure that you practice this again so that you get the same answers and it tallies both our answers. We have an additional problem of 3 numbers now, 48, 64 and 80. It remains the same ideally, right? So let us first find out the HCF. To find the HCF, it's pretty simple. 48. So 48, I will take 2, right? 2 2s are 4, 2 4s are 8, 2 12s are, then I have 2 6 are, 2 3s are, and 3 1s are, right? So I will write the factors here. 48's factors are 2 into 2 into 2 into 2 into I have 3. So these are the factors of 48. I will give you a very simple solution for LCM as well using these prime factorization alone, but when you are simply asked LCM for different numbers, make sure that you follow the previous method that was taught. Directly 3 numbers put together. So that gives you a better solution. Now coming to 64, 64 again, 2 3s are, 2s are, 2 1s are, I will take 6 here, 2 8s are, 2 4s are, 2 2s are, and 2 1s are. So this is giving me 64, which is 1 2 3 4 5 and 6. 2 into 2 into 2 into 2 into 2 into 2. So that gave me 6 2's. Next I have 80. Let's again find out. 2 40's are, next 2 20, 2 10, 2 5 and 5 1. Remember, it is a triangle. 5 1's are 5, 2 5's are 10, 2 10's are 20, 2 20's are 40, 2 40's are 80. So remember that one, only then you would be able to get similar answers. Anyways, coming back, 80 would be 1 2 3 4, we have 4 2's and 1 5, right? So this is how we've got the prime factorizations. Now let's erase this for our convenience. Now to find the HCF, I told you you need to bring the same number. So there we did it for 2 numbers, here we have to do it for 3 numbers. Now you have to find the same numbers. Let me take a different color so that it becomes easier. Let's take this. So I have 2 2 2. I have again 2 2 2 is here. I have 2's here. I also have 2's here. That's it. Do I have anything in common? No. So I will take 1 2 from here. I take another 2. I will take another 2 and this 2 again. So this is for HCF. So what did I get? 2 into 2 is 4. 4 into 2 is 8. 8 2's are 16. So HCF is 16. Now to find LCM, you can either go back to the same method that I showed you, because that was 2 numbers, so it was very easy for me to do it. But since I've already found out the HCF, you should know LCM is simply HCF into the remaining numbers. So the remaining numbers are 3 into 4 into 5. Why did I write 4? Because 2 into 2 is 4. So HCF is 16 into 3 into 4 into 5. 4, so 16 3s are 48 into 20. So multiply that. So 16 1s are, 2 4s are 8. I have 9. 960. So LCM of this is 960. So that is pretty simple for us to tell because this is the least common multiple. The common multiple meaning 960 is divisible by all these three numbers. It starts with 960, maybe 960 into 2 would be the next number. HCF is the highest common factor for all these three numbers. That means 16 into something is 64, 16 into something is 48, 16 into something is 80. So that's how it works for LCM and HCF. And when you're doing LCM, remember LCM is basically HCF of those numbers into the remaining numbers. So this is ideally going to give us the entire solution for LCM and HCF. So let's move on to the next topic, which is called the surds and indices. Essentially, surds are just irrational numbers which are expressed in the form of root x, right? So root x, what is the difference between an irrational and a rational number? So when I say rationals, I always write it in the form of p by q, where q is not equal to 0. Of course, this number, the irrational numbers are also essentially the same, but then again, these have a terminating value. For example, I say 1 by 2, which is just 0.5, right? But then again, I will have something like 10 by 3. So this is nothing but 3.33333. It keeps on going. So therefore, this could be called as an irrational number, while this becomes a rational number, which is essentially a fraction. So this is something that is supposed to be known. So that is what surds are. Surds are just in the form of this root x. For example, I can write root 2, I can write root 8, and then further let's say root 11, so on and so forth. So these are all surds. Now let's come to the exponential expressions. Exponential expressions are simply indices. So they are going to tell us something's power. For example, surds here, when I say root x, this means this root's value is power 1 by 2. So let's say I have third root of something, third root of x, I am trying to say that it means 1 by 3. So this power is known as our indices. And when I just talk about it arithmetically, this becomes base. And this becomes our exponent or simply indices. So that's how surds and indices work. Okay, so now let's understand the rules for search. So when I have to add or subtract or let's say multiply or divide, I will have to have some rules, right? For example, when I say for normal equations, when I say 10 minus 8 or let's say 100 minus 88, what do? We basically are borrowing a number from here and then it goes here, then this becomes 9 and then I get a number 10 there. So that's how borrows work. So that's how it works for the normal numbers, right? Normal numbers as in whole numbers or let's say natural numbers for that matter. Similarly, surds will also have some sort of properties or way of solving so that it becomes easier for us to go on and go flow with it. So let us understand how that works. First thing is, when you simplify, so this is simply root of a and root of b. So this is going to tell us that you can simply multiply all of them together provided your radical's value. Radical as in this root that we talk about. So that is our radical. So that radical has the same value. For example, let's say I have root 2 into root 3. So if you see, my radicals here are same. It's simply power 1 by 2 for both of them. So when such is the case, I can say it's 2 into 3, which is technically simply 6. So this is an example. You can see here as well. So this is root 5 here, which means root 3 into root 5 gives us root 15 because 3 into 5 is just simply 15. So that's how the first one works. Let's understand adding and subtracting surds. So there is something called as like surds and unlike surds. So let us understand a little bit about that. Like surds and unlike surds. Just like our algebraic expressions, when I say there are like terms, right, or I say unlike terms, what am I trying to say? I am saying, let's say I have 2x, 3x, 4x. When I have just these x's here, I can simply add or subtract them. But when I have, let's say, 2x square plus 2x, this is not possible because these expressions here are different. Just like that, it works for the like and unlike surds as well. So only like surds can be added or subtracted. That means the radicands are supposed to be the same. For example, here. So root 2 is here and root 2. So you will treat it as a same expression. So that becomes, so you will add this part of it. So 3 plus 2 becomes 5. 5 and root 2 remains the same. If I have to look at in the form of algebra, it is simply 3x plus 2x, which is going to give me 5x. In the place of x, what did we say? It is simply root of 2. So that's how like surds work. So you can only add and subtract like surds. Next we have multiplying a surd by a constant. So by a constant, it is simply, let's say there is a constant a and there is a surd. So all you have to do is, see, so you are adding this. So 3 into root 5. It is simply, let's say 3 into x gives us 3x. Similarly, 3 root 5, 3 into root 5 will give me 3 root 5. So this becomes a constant here. This works as the radicand that you see here. So that's how multiplying by a constant works. Let us understand the next part, rationalizing the denominator. Now for example, so when I say denominator, so this is how something looks like, right? So we generally do not write these kind of surds in the denominator. Therefore, what we do is we multiply and divide by the same. In mathematics, we are supposed to come back to our original logic, no matter what expressions or addition, subtraction, any operation that you do, you're supposed to come back to the original position. So what will I do? I will multiply and divide by root 2. So this is going to give me 1 and I am coming back to my original expression. So this is simply root 2 and root 2 into root 2 is simply 2. We will understand this better because I know 2 can be written as 1 by 2 here and this can also be written as 1 by 2, or simply I just told you, you can multiply like surds, so this will give me root 4 here. So I know root of 4 is a definite value which is 2. Therefore, whenever you have the same roots, it is going to give me this whole number that is present inside the radicand. So from here I get root 2 by 2. So originally you are trying to say root 2 by 2 is the upcycled version of 1 by root 2, or you can say 1 by root 2 is the simplification of this particular term. So that's how rationalizing works. I'll give you another example. I'll say 3 by root 8, right? So for this again, we have to multiply and divide by root 8. I am going to get 3 root 8 divided by simply 8. So that gives the denominator's rationalizing part. So you don't have to worry about different terms, more terms like this. So when such is the case, we will discuss what happens in the later scenarios. But as of now, this is the only part that you would have to understand. Next is surds and powers. So I just told you, let's say I have root 2 whole power of 2. I just told you that root 2's value is 1 by 2 whole power of 2. And from exponents, we know that whenever we have a power m whole power n, this becomes a power mn. So the bases are the same. When such is the case, when you have whole power, you will simply multiply the powers. So when you multiply these powers, 2 and 2 gets cancelled. I am going to be left out with 2. An easier example would be, let's say I have 16 power 3 by 4. So when such is the case, I know 16 can be written as 2 power 4 and totally this is 3 by 4. So what am I going to do? It is 2 power 4 into 3 by 4. So 4 and 4 gets cancelled. 2 cube is simply 8. So this is an easier example of understanding how surds and powers work. So it is simply basically root of 2 whole power. Even if I have 6, this is simply going to give me 2 power 1 by 2 whole power 6. 2 1s are and 3s are. This is simply 2 power 3, which is again 8. So you can see 8 can be written in multiple formats. 16 power 3 by 4 or root 2 power 6. So there are multiple ways of writing a single number, provided we understand how surds and indices work. So we just understood about the different rules for surds. Let us also understand rules for indices. Indices meaning powers. So first is the product rule. The product rule says you have, so this indicates power. We cannot write directly as a power m. So instead we write this as a power m like this. So it is just a generalized understanding. Okay, so let us understand as to how that works. So these are the bases. The a's that you see here are the bases. So when you have a power m into a power n, it is simply the addition of these. You have to understand that these are in multiplication, but the bases here are same. Only the powers are different. So when such is the case, you can simply write this as a power m plus n. Next is the quotient rule. Quotient rule meaning a power m divided by a power n. This is going to give me a power m minus n. Remember, when in multiplication this sums up, when in division it becomes a subtraction of that part. Next, I just told you about this. So a power m whole power n. When such is the case, you simply take a product of these two, a power m into n. For any 0 exponent rule, any number a power 0, this becomes 1. But you should always know, this is a very important thing, a is not equal to 0, because if I say a 0 power 0, this cannot be true, because in nothing power nothing becomes an something we are not able to understand. So nothing power nothing cannot be possible, hence a cannot be 0. That's when a non-zero term becomes 1. Negative exponent simply means a power minus m. This, to make it positive, we take it as 1 by a power m. Let's say I had this in the denominator. I had a power minus m. So to bring it upside, it simply would have become positive a power m. Next, fractional exponent rule. So this is a power 1 by n. I just told you in surds, whenever we are writing root 2, this simply means 2 power 1 by 2. Let's say I have cube root of 2, this again means 2 power 1 by 3. Similarly, if I have the nth root and a generalized term a, this simply becomes nth root of a. That is all you have to know. N can be any number starting from 1, and again 1th root does not exist. So it starts from 2nd root, which is root 1, and then a can be any number provided it has some certain value. So this is how the rules for indices work. For multiplication it becomes addition, for quotient it becomes negative, for a product you need to have whole powers. For a power 0, provided a is not equal to 0, becomes 1. The inverse works as a power minus 1, which is 1 by something, and the nth root is simply this. So this is how the rules for indices work. So we learned a lot of things about, addition, about numbers, surds and indices. We came through a lot of things, right? So now let's apply all of these into our problems now. These are all practice problems. We will practice one or two problems, and then we will all bring past paper problems so that it becomes easier for you to understand and analyze how exactly questions are going to be asked in the aptitude part of your examinations. So first things first, is 37 an even or odd number? Is it a prime number? So if you see, there are two questions provided in a single question. So they are saying, is 37 an even or odd number? That is our first question. The second part, again, is it a prime number? Let us not look at this as of now. Let us just concentrate on first part of the question. They are asking if it's even or odd. For even or odd, I clearly told you, if it's divisible by 2, only then it becomes an even number. If not, it is an odd number. So for divisibility by 2, we know it is 0, 2, 4, 6 and 8. The unit digits are supposed to be one of these. Is it this? It is not. So hence it is odd number. So you have this options B and D. One where it is prime, another where it is not prime. Now how do I find if it is prime or not? First things first, find a closer multiple of 37. Closest multiple is, let's say, 36 and add 2 to it, so it becomes 38. Is there any other number that can come between this? Simply 37. So of course I can say 37 is a prime number, because after this 36 can be written as 6 into 6, right? So 6 into 7 is giving me 42. So it jumps by 6 numbers. Now for 38 is simply 19 times 2. 19 times 2, right? So there is no number which is coming before that. Again, this would be 19 before this, but then 38 is the second multiple of 19. So there is no number which is coming in between that. Therefore, I can clearly say it is a prime number. So our option odd and prime would be the first solution for this. So coming to the next problem, very simple again, find the sum of the first 5 prime numbers. So these kind of questions, the first 3 numbers, first 5 prime numbers, these are some things that you are generally supposed to know to save your time. Hence, so for now we will just solve it, but make sure that you know the solutions for at least first 5 prime numbers, right? So let us understand what are the first 5 prime numbers are. I clearly told you one cannot be a prime number because there are 2 criteria for prime, one by itself and one has to be a factor of it. So one doesn't have it, therefore we start with 2, 2 plus 3 plus 5 plus 7, 9 cannot, and then I have 11. So now what are the sum of these? So this is going to give me 10 and this is 18. So 10 plus 18 is simply 28. So the solution is option A. Coming back to the third problem. So here the question is 567 divisible by 9? So they have clearly, so generally this is not given to us in the problems, but just for your understanding, we have just given it here. So let us understand as to how this works. So in divisibility rule, I clearly told you that for divisibility by 9, we have to sum each number, find the total sum of it and check if it is present in the 9's table or not, or if it's a multiple of 9 or not in simple terms, right? So let's do that. So 5 plus 6 plus 7. I know 5 plus 6 is 11, 11 plus 7 is simply 18. So clearly 18 is what? Is the second multiple of 9, therefore divisible by 9 is solution yes. Other solutions are saying no, only divisible by 3. Is it true? It is divisible by 9 and 3. So make sure you read the options as well. And only divisible by 6, that is also not possible, because if it's divisible by 3 and 2, only then it is divisible by 6. So hence our solution is simply a yes. Now next problem. A number ends in 0 is it divisible by 5, 2 or both? Now what are the options? Only 2, only 5, both 2 and 5, neither 2 nor 5, right? So for this we need to know these two's divisibility rules, right? One is 5, one is 2. For 5, I know the unit digit is supposed to be either 0 or 5. For 2, I know it is 0, 1, 2, 2, 4, 6 and 8. So it is supposed to be between these. So this 0 and 0 is here, right? So when there is a mix of these two, of course it is divisible by both 2 and 5, right? So I can say C is my option. So let us look at the problem number 5. This is a problem which is given from an aptitude question. So it says, find the remainder when 125 is divided by 7. So ideally, and this is a remainder theorem. So it is specified here saying you have to use the remainder theorem. Even if it was not specified, since we are finding the remainder of it, we will always use the remainder theorem. Now how does that work? I told you the divisor, the dividend, and finally we have the quotient coming out of this, and finally whatever remains is our remainder. So for this one we generalized it as n, x, q and r. And how did we write it as? We wrote x can be written as n into q plus r. Similarly, let us understand for this particular problem. So we are dividing 125 by 7. So now let us try and find this one. So for this 7 ones are 7. I have 5 coming out and then again 5. Then I know 7 sevens are 49. From this what will I get? I am going to get 6, right? So ideally, how does this look like? This is basically 125 is equal to 7 into 17 plus 6. So my remainder is clearly 6. So with more practice, you would be able to clearly tell. You will see this number 125, and since you know 7's multiple, one of the multiples is 17, so you can simply subtract that part and you will again get 6 as your final output. And always remember, whenever you are dividing a number by something, when I apply a remainder theorem, the final output is either equal to 7 or any number less than 7. So it starts with 0, 1, 2, 3, 4, 5 and 6. So let's say in the option you never had something below this. So all these numbers are all below 7. Let's say I did not have something like that. Let's say I had A as my option as 8 and 9. Here I had, let's say 7 again, and in the next option I had 6. So you did not even have to use the remainder theorem. All you would have done is any number which is less than 7, go tick mark it, right? But since all of these options are less than 7, we are trying to understand if it's actually true or not. So that's how remainder theorem works. So now again we have similar problem, but here we are not specified saying we are using the remainder theorem. But as soon as you see this, what did I tell you? I told you have to use the remainder theorem. So first things first, I am dividing 132 by 11, right? But if you look at it, can you say something about this? I know 11 into 10 is where my idea ends, right? 110, but this is more than 110. But I also told you, you have to know the squares until 30. So if you had known the squares until 30, you would know 11 into 11 is simply 121, right? And 132 is somewhere close to 11. So you simply add 11 here. What are you going to get? 132. So you know 132 is completely divisible by 11 because the very next, so 11 into 12 will ideally give you 132. So when such is the case, I know my answer could be 0, but let's verify if that is true or not. So here I have 1s are 11, 2, 2 and 12. So this is 0. So my remainder is again 0. So it is verified now. So all you have to do is know the square of it, and since it was very close to that number, add 11 to it and check. That's all you had to do. Now coming to the next problem, this is a very important type of problem. Mark this as important as you can, because this type of problems are always asked in any sort of aptitude that you are writing. So what is the unit digit of 7 power 45? I am not saying it is the same question that is going to be asked. I am only saying it's a similar question that is going to be asked. Generally, unit digit of something this huge is asked, right? It is impossible for us to sit and multiply using all of this, but the ideology remains the same. So first things first, you need to know what is 7 power 1. So it is 7 square. So this is the repeating number, like I said, unit digit, last digit. In that concept, we had discussed all of this. So let us again discuss that using the number 7. So 7 square is 49. 7 cube, as I said, you have to know cubes from 1 to 10. So this is 343. And 7 power 4 is simply a number which ends with 1, because 7 square, 9 into 9 would give me ideally 81, right? So 49, so I have a number 9 into 49, I have a number 9. So it is directly going to give me a number 1 in my units place. So it can be anything. We are not really concerned about that, since it is only the unit digits that is being asked here. Generally, it is always the unit digit that is asked, because everybody knows that you cannot sit and multiply all the numbers, right? So now coming back, so there are 4 different terms. Now when I get 5th term also, 7 power 5 also, it will again give me a repetition of 7 in my units digit. Again, when I come to 6, again it will give me a 9 in my units digit. So this is how it looks like. Now coming to understanding, so let's come to an understanding of 7 power 4. So what are we getting in the units places? It is either 1, 3, 7 or 9. So there are 4 terms here, right? So there are 4 terms that is there. But what is asked? 49. So for that, what you will do is find the remainder when divided by 4. What is the remainder that you are going to get? So let us try that out. We know 4 tens are 40, 4 11s are 41, 44, and then I am going to get the remainder as 1. So even if I do it this way, 4 ones are 4 and 5 is given 1, 4. My remainder here is simply 1. So this is 1, right? Remember this. What will I do about this? Take this to the power of 40. 45 is equivalent. So you should know 45, power 45 is equivalent to power 1. That means 7 power 45 unit place, 7 powers 45's unit place is equivalent to 1. So that means it is simply the number 7. I will repeat myself here. So first thing what you have to do is first find out 7 power 1, which is 7. 7 square is 49. 7 power 4, 7 cube is 343, and by general notion we know it is going to give me a unit place as 1. So now after this we know it is a circulating term. Since it's circulating, I know there are only 4 numbers. Instead of digits, I can say it's simply 4 numbers. Now what am I supposed to divide this with? 45. So 45, find the remainder of 45, or you can simply call it as modulus, because when I say divide, you're writing the quotient. I will call this as modulus. Modulus is written as this 4. This is going to give me 1 as my remainder. So when you find the remainder, after that what you do? You simply say 7 power 45's unit place is equivalent to 7 power 1's unit place. So it was very easy for us to find out what is the unit place of this, which is simply 7. So that's how this entire problem is supposed to be gone about. Okay. Now there is again a bit of a similar problem, but instead of powers, we simply have product of two numbers. Last digits, I told you last digit is the same as the unit digit. The product of 34 and 56. Let's take a simple number. I have 11 into 12. So this is just an example. So when I multiply these two, it is 2 into 1 and 2 into 1, which is 22. Again 1 into 1, 1 into 1. So we leave this space empty. 1 into 1 and 1 into 1. So I am technically getting 132. What happened? I only had to multiply this part with this part. Let's take a different highlighting color so it becomes easier for you to understand. So all I did was I multiplied this with this place to get my units place done. So we will do the same thing with this one as well. Here also. So 34 into 56. All I have to do is multiply this with this, which is simply 24. I don't use this, right? I don't use this because this goes as carry. All I need is this particular term, that is what I write. So therefore, my direct answer is simply 4. Okay. Now about the divisibility, that was done. So most of your problems are generally asked from those similar patterns, right? So if you have a different numbers term, you will have to first identify the circular pattern and then again apply the same thing, right? And for products, all you have to do is multiply the unit digits of the two terms that is given to you. Now, let us understand the HCF of two numbers. This was also a question that was asked in your previous papers. Now, to understand this, again, very simple, but then in my previous modules, what did we understand? We saw that we were prime factorizing each of them and then finding out the HCF, which was again a very lengthy task, but it gave us the simple solution for it. Now, we need, our main agenda in aptitude is to save time, because 50 questions in 50 minutes is not a joke. So you just get 1 minute for each question, and sometimes if you sit and do so many problems for each question, you sit and spend so much time for one question, then maybe a different question which you can tackle with just 2 minutes won't be possible, right? Hence what we do here is we use a different method to find the HCF of it. Now it would be the non-zero, remember this term, non-zero multiple, or instead of multiple I can actually use the term factor, non-zero factor, because there is a difference between multiple and factor. So let us use the term factor. Now why did I use this term factor? Let us understand. So first what you do is take the bigger number in the dividends position, write the smaller number in the divisors position, right? I know when I multiply 56 by 2 times, it will be more than 100. So therefore what will I do? I will simply write 56 now. Now when I subtract this, what am I going to get? 2 and 4, 42. Now what will you do? You will bring this term in the dividends position. So this becomes 56. Again, if I multiply this twice, it becomes more than 80. So therefore I will just take 1. So this gives me 42. What will I get? 4 and 1. Now what will you do? You will bring this for the dividends term. Now here I know the 3 times 14 is simply 42. What did I get? I got my remainder as 0. So I told you non-zero factor. What is the non-zero factor, simplest factor? This is 14. So 14 is the HCF of 56 and 98. How did I find that? Instead of prime factorizing all of these, what did I simply do? I simply took these two numbers. I took 98 in my dividends position, 56, and what did I get? 42. From here I put this 56 under the dividend position, 1 times 42, and then subtracted, and then since this was not 0, I brought this one back again. Until and unless I get that 0, we will keep following the same method. That's how it is easier for us to do the HCF and just the HCF part. So I hope this method was understood. Make sure you practice this often so that this becomes easier for you. So now let's go to the problem number 10. Now it says the LCM of two numbers is 72 and their HCF is 12. So with the first notion, we understood there are two numbers. Let's call those numbers X and Y. And their HCF is given as 12. One of the number is, LCM is given as 72. One of the number is 24. That means let's say I take X as 24, find the other number. All you have to do is find Y. Now to do this, I remember I told you when we were discussing HCF and LCM, HCF into LCM gives us product of two numbers, right? What are the two numbers? Again, X and Y. So from here, I will simply use the same part. So I was given HCF, right? HCF was given as 12, LCM was given as 72. I know one number is 24. Let's find out the other number. So I am going to write the same thing here. So for that, it is simply, so when I have something in multiplication, it goes to the other side, it becomes division. So I can write this as 12 into 72 by 24 equals Y. So to do this, I know 12 ones are 12, 12 twos are 24. And I can say 2 ones are 2, 2, 36 are 72. So clearly, Y's value is 36, which is our option B. I hope this was understood. So all you have to remember is, first thing is HCF into LCM is the product of the two terms that is given to you. Now this is also this question, this problem number 7. Take a minute to read this. It says if a number is divisible by both 2 and 5, what is the last digit of that particular number? Now for this, right, you have to apply two ways. One is divisibility, another one is LCM. I told you when applying LCMs for real life, what do? We combine certain terms, right? So that's how our application of LCMs work. So here we will do the same thing. We know this and this both are nothing but prime numbers. So the LCM of this is simply 10. We simply multiply those two. 5 into 2 becomes 10. Now, if a number is divisible by both 2 and 5, check, is 10 divisible by 2? Yes. Is 10 divisible by 5? Of course, yes. So, any number which is a multiple of this should ideally be divisible by 2 and 5 both. So, now, what is the last digit of that number? What should it be? It should be a multiple of 10 alone, so that it is a multiple of both 2 and 5. So what would be the unit digit? We know divisibility by 10. In the units place, it only has zeros. So therefore, unit digit would be 0. So 0 is my final solution for this. Options are not given to you because these were subjective questions. All you have to do is find the LCM of this, and units place you will just write divisibility by 10. And we know divisibility by 10, units place is simply 0, so therefore 0. So that's how this question works. So there are similar questions like this. We will make sure to give it to you so that you make sure to solve all of them and crack your interviews well and better. Now if you read this problem, take a moment, understand this. We happen to solve 7 power 45, which was a similar question as this. Here the only difference is this is 13 power 50. So for that, see, what will you actually need? So when we are multiplying something, it is simply the units place that is working for us. So here the unit place is simply 3. So I only have to know the units place of 3 alone. So 3 power 1 is 3, 3 square is 9, 3 cube is 27 and 3 power 4 is 81. Now again, after 1, 2, 3, 4, it again repeats itself. So therefore what happens? I will only be considering these 4 terms, right? Now this is a circular pattern. All we have to do is we have to divide this by 4. So we have to divide it by 4, and whatever the remainder you get would ideally, you will check for which one it matches, and then you will write that is the unit digit of that particular term. So 50 divided by 4, let us do that. 50, we are dividing it by 4, ones are 4, 10, closest is 2, 8, so which is 2. So therefore that means 13 per 50's unit place is equivalent to this. So 13, or simply 3 power 2. 3 powers 2's unit place. Now what is 3 power 2's unit place? It is 9 here. So therefore the unit digit of this is 9. We are not bothered about the other digits. We are only calculating the last digit of that particular number. Why? Because that is what is asked. And anybody who wants to interview you just wants you to think this way, and they just want to have a conversation with you. And if you're actually willing to work for them, it's not like they're trying to know if you know the complete math behind this. No, that's not how it works. It's simply if you have the analytical mind to analyze all of this, because now you can't sit and do 13 cube, 13 power 4, you can't do all of that. Instead, you have the common sense saying it's simply 3 here. So if I multiply it multiple times, it is simply going to give me the 3's unit place alone. So therefore, we will use this solution of it, and it gives you answer in what? Less than 30 seconds with more practice, right? So unit place here gives us 9. So now let's move on to problem number 13. They say two numbers have a HCF of 7 and an LCM of 84. If one number is 14, find the other number. So again, we use the same logic. HCF into LCM equals product of two numbers, right? So HCF is given as 7, LCM is given as 84. To one of the number is 4, another number, let's say, is x. So what do we have to do? We know x can be written as 7 into 84 by 14. So 7 ones are, 7 twos are, 2 ones are, 2 42s are. So our final solution is x is equal to 42. That means our second number is simply 42. So all you have to do is you have to remember this part. Otherwise, there is a huge part of the solution. So make sure these terms are marked in your book. You practice these on a regular basis. So now we have problem number 14. It says simplify root power 6. Again, very simple. All we have to do is we can say it is 1 by 2 because it's a radical, and 6. From here I told you in indices, when we have something power, it is a multiplication of those two. So this is simply 2 power 6 by 2, right? So 2 ones are, 2 threes are. So what is 2 power 3? It is simply 8. So this is my final solution. So root 2 power 6 is nothing but simply 8. The last problem for this entire module is simplification of 16 power 3 by 4. So 16 power 3 by 4 is a very simple solution. So 16 here can be written as, so if we didn't know 16 was 2 power 4, then I would have had to multiply and then take the fourth root of it. That doesn't work. That is not at all required. So I'll say 16 is what? 2 power 4 whole power 3 by 4. Now again we multiply, 4 and 4 gone. Again my final solution is simply 8. So that's how it works for 16 power 3 by 4. So with that we have come to an end of this entire module of understanding numbers and how it works. So here what all did we study? Let's have a quick recap. We understood basics of number, odd, even and prime numbers. We saw divisibility rules for 2, 3, 5, 7, we saw 8, we saw 10, we also saw 9, we saw 11. 13 and all of that, you simply divide all of that and you will get it. Then we saw the remainder theorem. In remainder theorem, we saw different types of remainder theorem for how it can be used for polynomial, how it can be used for single numbers and all of that. We saw what is the relation between unit digit and last digit and how it is helpful for us to understand for huge powers. We also saw factors and multiples. We understood the definitions. We also did a lot of problems of HCF and LCM. And we also saw surds and indices, and furthermore, we solved the problems. I hope you have understood the entire module. If there are any questions, you can always reach back to us. Make sure you're practicing a lot. We have a lot of questions built in for you. So make sure you're practicing that on a regular basis. If you do that, you would definitely succeed in your interviews. Hope you do well, and all the best.